Hi everybody. Remember last time we solved infinitely long wire on which the charges are distributed homogeneously, okay? And if we get a segment dy, the distance to the point of concern, which is point P, the distance was given by r, where this is x and this is y. This is two-dimensional problem, okay? And the effect of this dq in this small region is dE, and it's given by k dq over r squared general expression. And also we used lambda, okay, lambda, which is dq over dy. This is done in order to go from dq integration to dy integration, because dq will be, in this case, lambda times dy. So lambda is just a factor that we are using, okay? Usually, if this has a finite length, instead of dq over dy, you can also take total q divided by total distance, okay? For some problems which have finite length, we can use this expression. Anyway, so last time we have seen that the distance, okay, this side has exactly the symmetric side on negative y, and then this produces an electric field in this direction, and their y components will cancel each other, so that the only components which survive will be the x components, so that we will get the electric field as dE cosine theta, okay? dE times cosine theta, this is the x component of the electric field, okay? So the total electric field after the integration of all these contributions will be given by this expression. So if you put dE here, also insert dq, this is what we get, okay? This is what we get. As you see, this is a y integration, but not easy to solve because there is theta also, so that you have to convert this into x and y, which can be done because cosine theta is given by x over r, but it's x over square root of x squared plus y squared. You can do that here also. In this case, it turns out to be a y integration, which is very difficult to solve without using the integral table. So we said that let's do this in opposite case, where we can maybe go to the theta integration from y integration. In order to do this, we have to go from dy to d theta, and the way to do this is just using tangent theta, because x is constant in this case. If you differentiate this expression on both sides, left-hand side will give you dy, the right-hand side will be x over, okay, so cosine square theta d theta, because the derivative of tangent theta is cosine square theta. So also x squared plus y squared is x squared over cosine square theta, because of the fact that cosine theta is x over square root of this. If you just square both sides, you will see that if you replace this x squared plus y squared by cosine theta, which is squared, of course, then it will give you this. So when you insert everything, you see that you end up with this kind of very simple integration where cosine square thetas cancel. In this case, we said that the limits would be from minus pi over 2 to pi over 2. The reason was that because for infinitely long distances above the x axis, so we will have 90 degrees, but below minus 90 degrees. So this is what we said. This is for the symmetric case. And then because the integral of cosine theta is sine theta, when you put these limits, you end up with a factor of 2, and then the result was 2k lambda over x, okay? You will remember this. Okay, so this was the result that we found, but now let's change this problem into something that is finite. For instance, suppose that we have now finite length of this rod, okay, and its length totally is given by L, and then this is x-axis, and we would like to again find the electric field. Again, we do the same thing. Since this is y-axis, we say this is dy, inside there is dq, and of course all plus. The effect of this segment at this point will be this way, but now y components will not be able to cancel each other because there is no other part below the x-axis, so that this will have two components, dE cosine theta, and this will be dE sine theta. Sine theta. Okay. So now this is dEx and this is dEy. So we should be able to find the x components and y components separately. So Ex will be just integral dEx or just dE cosine theta. But dE is again k dq over r squared, k times dq over r squared and cosine theta, and Ey will be similarly given by k dq sine theta divided by r squared. Again, from dq to dy we can use this, and from dy to d theta we will use this expression. And if you do the similar analysis, we will see that the resulting will be just electric field will be equal to of course Ex times I plus Ey times J, right? This is the total electric field at this point, which is the total electric field in this direction. Okay, so but this will be a function of x again. So the distance is x there, and the distance here is y, but the total of the rod is just L. Don't forget. So if you put these two terms here, you will see that the electric field is given as just simply k lambda over x, just like before. Okay, so integral sign cosine theta d theta minus sine theta d theta. Why there is a minus sign? Because y component of this electric field is negative. So this Ey is negative. This is the reason that we are using this minus sign. Okay, because the vector should be downward. Okay, so this is the integral we have. Remember that it was earlier from minus pi half to pi half, but now this angle theta is from 0 to maximum possible theta. Okay, so maximum possible theta is just given as theta 0. So now for theta 0, I can do from geometry, this is x, this is L, and this is maximum theta 0. And as you see, sine theta 0 is equal to L over R. Of course, this is always R. And then cosine theta 0 is just x over R. Okay? And in this case, this R will be equal to square root of L squared plus x squared. Okay? So L over square root of L squared plus x squared. And similarly, this will be x over the same denominator. Okay? So now the integral of cosine theta is sine theta, but the integral of minus sine theta is cosine theta. So if you just put these things in, you will end up with just the result will be k lambda over x sine theta from 0 to theta 0, and then plus, because the derivative of integral of minus sine theta is plus cosine theta. Cosine theta, okay, from 0 to theta 0. Please do not make a mistake like that. You have to put a parenthesis sign to multiply this term also by this. Okay, so now we have to put I there and J there. Okay, because the left hand side is a vector, you have to be able to place these vector sign, this unit vectors correctly. So the result will be just k lambda over x. Okay, sine theta 0. Sine 0 is 0, but this will give you the result cosine theta 0 minus 1, because cosine 0 is 1, right? And here again, I there and J there. And for cosine theta 0 and sine theta 0, you can use these values. And then write everything in terms of L and X, as you see. So the electric field in this, at this point, will be given by this expression. So the direction will change, as you see. If you change this X, for instance, if you go here, maybe this direction will change into this kind of direction. Or if it is here, then maybe the angle will change. So if you go from very near values to very far away values, the electric field direction will also change, because there will be changes in X and Y components. Okay. Not only that, but also for very small distances of X, let's see what happens. For very small distances of X here, okay, for very small distances of X, you should be able to consider these values, sine theta 0 and cosine theta 0, and you can really see what happens to these expressions with X, of course, on the denominator. If you put this X on the denominator, then you can get their values in the limit and see what happens. It looks like when you are here, this electric field, when X equals 0, the electric field blows up. Okay. Anyway, so this is something that I wanted to give you as an extension for this problem. And sometimes we ask this kind of problem in the exam. So this is how you can solve it. Now, I stop recording and let you again ask me the questions if you have any.